All right, today we're going to talk about the characteristic equation of All right, today we're going to start with the characteristic equation, which is the easier way to go about finding eigenvalues. So, previously we were either given an eigenvalue and said, show this is an eigenvalue, or test and see, is this an eigenvalue? And today we're going to do how do you find them in a more generic sense. So we talked about before, if A was a square matrix and U is a non-zero, or A is, words are hard, U is not the zero vector and it's in the null space, that means U is an eigenvector of A, associated with the eigenvalue of 0. So sometimes this was just a very specific case. Now, this is what's actually a little bit more useful. If A is invertible, or A is invertible if and only if 0 is not an eigenvalue. Which means if 0 is an eigenvalue, then A is singular, which means it's not invertible. So that's just something nice you can use while looking at matrices and trying to figure out, okay, what do I know about them? And the proof is pretty easy. If the rank is n, the nullity is 0. That means null A is 0. And that means 0 is not an eigenvalue. So through all those if and only ifs, you're able just to chain these together. So you start with A is invertible, and we just go through what that means. And remember, rank was how many pivot columns did you have. So if it's a n by n and you have n pivot columns, that means there's no free variables, which means your null space has a dimension of 0. So we've kind of it's one of those things where we don't actually straight out say what it was, but we were kind of alluding to it. So anytime we've talked about the null of A not being equal to 0, we've kind of talked about the eigenspace without actually discussing it. So determinants are going to be kind of our key way of how do I solve this. So using our contrapositive that if A is singular, then 0 is an eigenvalue, we get the corollary that 0 is an eigenvalue of A if the determinant of A is equal to 0. Or if and only if, I should say. But where that comes in handy is I can look at that and just immediately say, okay, well, if I took the determinant, I could already determine one eigenvalue or rule out one eigenvalue depending on what my result is. More generally, and this is kind of our key equation that we're going to use a lot. If lambda is an eigenvalue, then the determinant of that matrix minus lambda I will equal 0. So this was what we were doing beforehand, but now we're going to just leave it kind of in a generic format. So beforehand, we used just, I think, this part of the equation where we would say, do I get a non-trivial solution, and what's the vector that's associated with that? Go back to your determinant rules just as a quick review because these are going to come in handy. So determinant of AB is the determinant of A times the determinant of B. The determinant of A transpose is the same as the determinant of A. The determinant of A inverse is just the reciprocal of the determinant of A. And if A is triangular, which remember means it's got to be square, and either everything above or everything below the main diagonal is zeros, then it's just the product of the diagonal elements. And so remember, if it's a 2 by 2, we have our quick little shortcut here. If it's a 3 by 3, then you have to take into account, you have to do either the cofactor expansion, or there was the shortcut that I showed y'all where you write the first row and the first column and the second column again. And then after you do that, then you would just kind of do the connect the dots thing. But if you prefer to do the cofactor expansion, just do that. I don't have a preference either way. As long as you get the right answer. That's all I care about. So, first things first. What are the eigenvalues of this 6 by 6 matrix? Now, taking a look at it, remember we said that if the matrix was upper or lower triangular, then the then the determinant was just the product of the diagonal. Well, remember this is going to be, if I want to find the eigenvalues, I do minus lambda I, which means every diagonal I'm going to have to subtract lambda I from. Or just lambda, sorry. Which, if you do this determinant, what you're going to find is everything's just going to come out to be the product. If you do the determinant, then following that rule of this is upper triangular, it's just going to be the product of the diagonal elements. So what that means is if I were to take the determinant of this, all I'm going to get out of it is, well, let's see, 5 minus lambda shows up twice, so I'll have 5 minus lambda squared. Negative 7 minus lambda shows up 3 times. So negative 7 minus lambda cubed. And then negative 1 minus lambda only shows up once. So that means our eigenvalues are 5, negative 1, and negative 7. Now, those are the unique eigenvalues. Technically, our eigenvalues are 5, negative 1, negative 7, negative 7, negative 7, and 5. Because you're going to have as many eigenvalues as there are rows and columns. So this is a 6 by 6, so I should get 6 eigenvalues. However, if you want to say there's 5 is an eigenvalue with a multiplicity of 2, negative 1 is an eigenvalue with a multiplicity of 1, and negative 7 is an eigenvalue with a multiplicity of 3. That works as well. So you could say 5 with a multiplicity of 2, negative 1, multiplicity of 1, and negative 7, multiplicity of 3. That would be an alternate way to write these as well, because you do want to keep in mind that the amount of times they show up is important, because it means that that eigenvalue has a different effect. So, and what I mean by different effect, I should be a little bit clearer. It means that multiplicity also plays into, think about your row reduction. Negative 7 if you use that as your eigenvalue, that's going to take out 1, 2, 3 different pivots. So that's going to introduce more free variables, which means it could have more, what's the best way to put it? If you take these out, these would become zeros. So that means this is a pivot. So that's a pivot. That would become a pivot. If this is 0, then those are your pivot columns now. So you have 1, 2, 3, 4, 5. So you've introduced a new pivot column to that position. So just be aware that the multiplicities are important and you do need to keep up with them. Now, a word of warning. So remember we talked about if you multiply a row by a factor or by a constant, then to keep the determinants the same, you have to multiply by 1 over that factor. So if you say you multiplied row 3, let's say you were working with A and you multiplied row 3 by 4, that means that the determinant of A needs to equal 1 over 4 times the determinant of B. So if B is the row or is the new matrix, when you're doing the determinant, you're going to have to multiply by a 1/4 out front to counteract that. Interchanging rows is nice. All you got to do is just, if you change a row, if you change out 2 rows, just stick a negative out front. And this applies to however many times you change rows. If you change rows, do a little bit more, and then change rows again, that's a -1 and another -1. It's not just the first time you change rows. It's every time you change them. But the nice thing is kind of going back to the idea that if 2 matrices are row equivalent, they have the same solution. In this case, if 2 matrices are row equivalent, they have the same determinant. So you can do row reduction on a matrix to get a little bit nicer, and you'll still get the same determinant. Now, this you have to be very careful of. It's an efficient way to compute determinants because you can just turn something into a triangular matrix and then just take the determinant of that, which means just multiply the diagonal, which is not too bad. So this is where, though, you have to be very, very careful. All right, so then if we find the determinant of this one, we get -1 minus lambda, 4 minus lambda, minus -6, which is then going to equal lambda squared, -4 lambda, and this will be plus lambda, so minus 3 lambda, minus 4, add 6, so that's going to be lambda squared minus 3 lambda plus 2, which that factors into lambda minus 1 and lambda minus 2. So my eigenvalues for this one are +1 and +2. Because remember, you set this equal to 0. So it's like finding roots of a polynomial. Actually, in a second, I'm going to basically tell you that's exactly what it is. It's just finding roots of a polynomial. However, and this is where you have to be very careful. Notice with this one, this is just if I did 2 times row 1, add that to row 2, and put that into row 2. That's what I have here. So 2 row equivalent matrices will have the same eigenvalues. Or sorry, will have the same determinant. But, and this is a very big and important thing to keep in mind, if you row reduce the matrix and then take the eigenvalues, this happens. So then we get -1 minus lambda times -2 minus lambda. And then that's going to be, actually technically that should be a minus, minus 0. But that just gives us -1 minus, or negative lambda minus 1. I guess I can rewrite it like that. And then it also gives us negative lambda minus 2 to set equal to 0, which that means our eigenvalues are actually -1 and -2. So row reduction and then taking the then finding the eigenvalues yielded different results. So you have to be careful of that. Do not row reduce, then find the eigenvalues. It doesn't work out that way. You can row reduce to find the determinant as long as you follow the above rules. But you cannot, and I repeat, you cannot row reduce, then find eigenvalues. You're finding eigenvalues of a different matrix. They may be row equivalent, but they are not the same. And that's what you have to be careful of. Now, let's say I said I was going to find the determinant of A and then decided to row reduce. So notice with this one, I would do 2 times row 1, add that to row 2. And if I do that, I get -1 minus lambda times -2 minus lambda. That's going to be minus 6 lambda, which would be lambda squared. This would be plus 3 lambda. And then plus 2 minus 6 lambda, which then would give us, just making sure I got enough room, that one gives us lambda squared minus 6 lambda plus 2 to set equal to 0. Or minus 3 lambda, sorry. Because we combine the -6 lambda and the 3 lambda together. Which now, this is good because these two are the same. Which means they're going to have the same eigenvalues. So you can't row reduce and then find the eigenvalues. You have to say that you're finding the eigenvalues. Then if you want to row reduce, you can. Sometimes it might make life a little bit easier. A lot of times you just kind of have to stick it out for the long haul. So just be aware of that. If you row reduce and then find the determinant, they're going to be the same. But if you row reduce and then find the eigenvalues, you're going to find a difference. And this is one of those things, don't look at a coincidence as a certain fact. Because with this one, notice we got 1 and 2. And then when we row reduce, we got -1 and -2. It's not always going to happen like that. This is just one example. And one example does not constitute an entire rule. So don't think about, oh, well, if I just multiply it by this at the end. No. Always keep to that rule. Take the determinant first. Fine. But if you're going to find eigenvalues, you can't row reduce. You have to, if you're going to find the values of A, it has to be A in its original form. It can't be A after it's been row reduced a time or two. So just because they're equivalent does not mean their eigenvalues are equal. That's the takeaway. So one thing that you'll get is, and this is what I was talking about before, basically every eigenvalue problem is just going to turn into factoring. and then it's just going to turn into some matrix multiple or some row reduction. So if I were to write out our equation, typically we're going to have lambda minus root 1, and that's going to be to the k sub 1 power. And then you'd have lambda minus root 2 to the k sub 2. And then eventually down to lambda minus r, we'll say j to the k sub j power. And if you're wondering, well, why don't you just write whatever? Because what I'm doing is saying this. I want k1 plus k2 add up to k sub j to equal n. So basically, I'm just trying to rewrite this as a factored polynomial. So this is an nth. So basically, it's an nth degree polynomial. And I should state that it's factored. And it has n roots counting multiplicities and imaginary / complex. So basically, if you compare the two, they're the same thing. If I'm trying to find the eigenvalues of an n by n matrix, really what I'm saying is, what's this characteristic polynomial? And that's what we're going to call it. So the algebraic multiplicity of an eigenvalue is its multiplicity as a root of the characteristic polynomial. And your characteristic polynomial is always going to be what you get after you do this determinant. So this is what yields the characteristic polynomial. So this is what I meant. Basically, when you're finding eigenvalues, it turns into, can you factor the equation? Now, the thing to be careful of and pay attention to, all of these are, you're always going to have n roots because it's an n degree polynomial / an n by n matrix. If you have an imaginary root, and more specifically, if you have that all the roots are imaginary, the takeaway from that is the function, or there are no real eigenvalues. And what that means is, remember the point of an eigenvalue was that multiplying by your matrix A was the same as multiplying by a scalar lambda. That's the whole point of this. If you do AX equals lambda X, then that means lambda is an eigenvalue. It takes matrix multiplication and turns it into just scalar multiplication. So if it's imaginary, that means that it does have an eigenvalue, it's just not a real one, which is kind of a, yeah, duh, that's what an imaginary number is. But the key takeaway is that there is no, or the value you found does not have that effect of scalar multiplication and multiplying by the matrix A being the same thing. That's the key takeaway. So take this one for example. So this one's already upper triangular. So I already know my eigenvalues. It's going to be 1 and 1. Because otherwise I'm going to get 1 minus lambda, 1, 0, and 1 minus lambda. And then when I do that determinant, I'm going to get 1 minus lambda. Let me make that look less like a 2. 1 minus lambda squared minus 0. So we just get 1 minus lambda squared set equal to 0. So the multiplicity of the eigenvalues, well, 2. It shows up twice. To find your associated eigenvector, we do 1 minus 1, 1, 0, and 1 minus 1. And then, sorry about that, we should augment that. Or this one's actually equal. So we get 0, 1, 0, 0. And those are all set equal to 0. So notice here, x1 is a free variable, and x2 is equal to 0. So our associated, if we were to try and write this as an eigenvector, that means that we have x is equal to 1, 0, and then we could say multiplied by x1. Because x2 is 0, so that eigenvalue, or eigenvector, I should say, doesn't really exist. So our eigenvector is just 1, 0. We only have that one eigenvector. So the dimension of our eigenspace is actually 1 in this case, because we have, well, one free variable, and we have one we have one column. The number of eigenvectors you get will tell you how many the number of eigenvectors you have will tell you what the dimension of the eigenspace is. More specifically, it's the number of independent eigenvectors. So if you had 3 columns or 3 eigenvectors, but they were all 1, 0, 1, 0, and 1, 0, your dimension of the eigenspace is still 1, not 3. So if we talk about this one, our eigenvalues are, again, pretty straightforward. So if I do 1 minus lambda, 0, and then I do 1 minus lambda like that, I take the determinant, I just get 1 minus lambda squared minus 0 again. So I still have a multiplicity of 2. However, when I find my eigenvectors for this one, this is where things are interesting. Because remember, we plug in lambda is 1 here, so I'll get 1 minus 1, 0, 0, 1 minus 1, augment that. So that's equal to everything zeros. So what that means is both x1 and x2 are free variables. So that means our vector x is 1, 0 times x1 plus 0, 1 times x2. So we actually have two eigenvectors here, 1, 0 and 0, 1. So the dimension of our eigenspace here is 2. And again, it's the number of independent eigenvectors. If this had been 1, 0, 0, 1, and then we'd had 0, 0, or sorry, 0, 0 wouldn't work, but say 0, 1 had popped up again. Or I tried to add in 1, 1. 1, 1 is a linear combination of these two vectors, so it wouldn't work. So don't confuse algebraic multiplicity, which is, again, go back to if it's a factored polynomial, your algebraic multiplicity is how many times is the root repeated. Your geometric multiplicity is how many, or is what's the dimension of the eigenspace, which is how many independent vectors, eigenvectors are there that are produced from here. So just something to keep in mind. Now, we've got a couple more examples for eigenvalues. So, and again, if you want to pause it and give it a shot, go for it. So, first of all, the eigenvalues of this equation are going to be a little bit more interesting. Because if I do 1 minus lambda, negative 1, and then I do negative 2, and I do 2 minus lambda, I do that determinant. You may already be looking at this going, well, the first matrix is just, or the first vector is just negative 1 times the second, or vice versa, which is true. So that means the columns are not, or that means the columns are not independent, which means they're dependent. So let's continue on with this one, though. So I'm going to get 1 minus lambda times 2 minus lambda. This would be minus a positive 2, so just minus 2. So we'd set that equal to 0. If I multiply all this out, I would get lambda squared 1 times negative lambda, and then 2 times negative lambda, so minus 3 lambda. And then, yeah, plus 2. But then we also have the minus 2. So that means we have just lambda squared minus 3 lambda. So we get lambda squared minus 3 lambda equals 0, which means I can factor out a lambda here and get lambda times lambda minus 3 is equal to 0. And when you look at that, we have that lambda is equal to 0 and positive 3. So remember, we specifically said if 0 is an eigenvalue, then that means the matrix is not invertible. So we know the given matrix is not invertible. So that came from finding the eigenvalues. Now, the multiplicities are just 1 and 1. Each one only shows up once, so you're okay with that. Now, one quick thing in here. geometric multiplicity of lambda is equal to, or the specifics of the geometric multiplicity of lambda. What I'm specifically referring to here is that I don't say, okay, I got two different eigenvectors and then put them to add up how many, what's the best way to put it? I don't add up how many independent vectors I get and say, oh, if I get two independent vectors from two different eigenvalues, I don't say that it's got an eigenspace of 2. This lambda is specific to whichever lambda you used. So specific lambda. So not sum of all. So let's just find the eigenvector for 3. So I would get 1 minus 3, which would be -2. And then I would get -2, or 2 minus 3, which would be -1. Augment that, which is going to be rho equivalent to -2, -1, 0, and then 0, 0, 0. So that means I get -2 x1 minus x2 equals 0. And I also have that x2 is a free variable. So then we have x1 is equal to -1/2 x2, and x2 is, well, x2. So we get x equals 1/2 and 1 times x1. So that means we have an associated eigenvector here of 1/2 and 1. So the dimension of the eigenspace is 1, associated with the geometric multiplicity of 3. Now I have one more example, so I won't find, well, I'll work it up here. So if we use 0 for our eigenvalue, that just means we have 1, -1, or -2, -1, 2, 0, 0, which is going to be rho equivalent to 1, -1, those become zeros. So that means we have x1 equals x2, and that x2 is x2. Which means that we have the eigenvector 1, 1, which means that has an associated eigenspace of 1 with the eigenvalue of 0. So you can see that as you pick different ones, or sorry, not as you pick different ones, as you pick these, you're going to have the possibility of getting different dimensions. So the dimension of the eigenspace is not 2. The dimension of each eigenspace is 1. So always keep that in mind. Now, this second one is I picked specifically to show off what happens if we get imaginary roots. So we get 1 minus lambda. Of course, we're doing the determinant. 4, 1 minus lambda, -2. So I get 1 minus lambda squared. And if you can't tell, I made sure I wanted to keep the algebra easy for me. So this would be 1 minus lambda squared sorry, just double checking the calculation, plus 8. I want to set that equal to 0. So then I get lambda squared minus 2 lambda plus 1 plus 8 equals 0. So now I'm stuck with lambda squared minus 2 lambda plus 9 equals 0. That doesn't factor nicely, so go back to the quadratic formula. 2 plus or minus square root. B squared is 4 minus 4ac. So 4 times 1 times 9, so minus 36. All over 2 times a. A is 1. So that means we get 2 plus or minus I times the square root of 32. All over 2. 32 is square root of 4 times 8. Oh. Which is just 16 times 2. Let's not make this harder than it needs to be. So that means lambda is equal to 2 plus or minus 4 I times the square root of 2. And that's all divided by 2, which is going to give us 1 plus or minus 2I square roots of 2. Or you could say I times 2 square roots of 2, whichever way. So these, again, both only have a multiplicity of 1. But remember, our matrix A is in R 2 by 2. We don't just use R for the fun of it. R means that it has real coefficients. We just got imaginary eigenvalues, so there's no eigenvectors. We have no eigenspace to talk about because we're not looking at a multiplicity in this case. So if you get eigenvalues that are imaginary, you don't go through with that part, or you don't keep that part and say, okay, well, this eigenvalue is, or I'm going to find an eigenvector for this. Do not try and find eigenvectors for imaginary roots. I promise you, you're not going to have fun. And it's not going to work out in the end anyway because, well, you're trying to cancel out these imaginary parts, which means you're still kind of introducing imaginary parts. But our coefficients have to be real. Again, hence why we say it's in R 2 by 2, because we want to only include matrices that have real coefficients. If our matrix was in C 2 by 2, what I mean by that is if you have this, that allows for complex coefficients. So allows complex, or I should say complex entries in your matrix. But because we're dealing with R 2 by 2, we can only have real valued entries. So just keep that in mind. All right, so that was a lot of examples on how do we find eigenvalues, and what do you do to find eigenvalues, and then how do you find eigenvectors, and then what do you do about the eigenspace. So that's pretty much it for eigenvalues and eigenvectors in this course. They will come up a little bit, but we're going to use them more as a tool than just let's go find eigenvectors later on. So don't forget them. They're useful, and they actually do kind of come up in some other spaces. and not just in Avengers Endgame. So keep in mind just how to find them. And again, I basically showed you it's just factoring polynomials. So this goes right back to high school algebra for a brief moment. So it's not too bad. So I'll see y'all for the next lecture.